So we've been casually talking about the definite integral related to area. Let's make that a little clearer. So if we want to interpret the definite integral as an area, we can do it in this way. All right, if f is continuous and non-negative on AB, then the area of the region bounded by the graph of f, the x-axis, and the vertical lines x equals a and x equals b is the definite integral. The definite integral from a to b of f of x dx. In other words, we have what's over here in the picture. The definite integral from a to b of f of x dx gives us this area, all right, bounded by the graph of f, the x-axis, and the lines x equals a and x equals b. All right, so that's what it's saying. Now we're going to see in the future that, so right now we've just limited ourselves to non-negative functions. We're going to see in the future that if we go above and below, the idea is that if we're still going from left to right, that this is going to be considered positive area and this is going to be considered negative area. We're still going to be talking about areas, but when we add it all up, we're going to really be talking about the net area that's above the x-axis, as long as we're going from left to right. So for now, though, we're just concerned about area above the x-axis. All right. So let's see how we could use this in order to make a calculation. So here we have this definite integral from 0 to 4 of x dx. And we've talked about wanting to be able to evaluate this thing. So we can do it by area, possibly. In this case, we can. So let's take a look at this integral. So really what it's saying is we've got the function f of x equals x, or in other words, y equals x from x equals 0 to x equals 4. Okay, well, what's that? Let's just look graphically. That's just the line y equals x, which we're going to go from 0, and let's say 1, 2, 3, 4, to 4. All right. So that's what we're doing here. And there is the area that we're calculating. Now, obviously, I can see that this base of this triangle is 4. But what is the height? Well, remember, if this is y equals x and x equals 4, then y must also equal 4. All right, so we, in this case, also have a height of 4. So our area is the area of this triangle, which would be 1/2 base times height, or in other words, 1/2 4 times 4, which gives us 8. So we found the area is 8, and so we've actually solved that the integral from 0 to 4 of x dx equals 8. So we were able to calculate the definite integral through area. Now, this is not always going to be possible, because we're not always going to have a region that is geometrically something that we know an area calculation for. If it is, then yes, certainly we can do it just like we did here, with a triangle or a rectangle or a circle or something where we know an area calculation. So we're going to need another way of doing this, but this is an idea that we can use. Okay, so let's recap what we've looked at. So we started with the idea that we were just looking for the area of a region, some area between a and b under some curve of some function. All right, so then we said, okay, if you wanted that area, what you could do would be to approximate it by doing equal subdivisions. So all of these subdivisions of delta x, and then make try and make rectangles out of them. All right, as such, and add up the areas of all the rectangles and get an approximation. So that was the first thing we did, and then the idea was we saw that Riemann said, okay, we could also do that approximation by doing different width subintervals, and then we wouldn't have to say use a right endpoint or something. We could use whatever point we wanted to determine the height of the rectangle. So we do that, and so still we have a bunch of rectangle areas added up to get a Riemann approximation. Okay, so then what these have in common is they're approximations. And the idea is that if we do a limit, then we can get to the definite integral. So the exact area represented, at least now, by this definite integral. So that's good, but we either have to do some sort of limit on it or use some sort of area calculation if we can. But what we'd really like to do, our goal is to generalize this. We want to generalize a definite integral as some expression to be evaluated without doing a limit directly and without going to geometric area formulas. And that's where the fundamental theorem of calculus, FTC, is going to come into play. That's the next thing that we have to look at. So let's do a few problems on the definite integral here. In this first one, we just want to write the definite integral that would give, as a result, the area in this region here, so this area in here, right? Evaluating just the integral. So it's the definite integral, so it's the integral of some function with respect to the variable, and we'll do it in terms of x. So the function we're integrating is obviously sine x, and we see that we're starting here at 0 and going to pi, so 0 to pi. That's it. The integral 0 to pi, from 0 to pi of sine x dx. Okay, now we're going to translate this limit of a Riemann sum into a definite integral. So again, this just means we're going to take the integral from 2 to 5 of some function dx. But here's our function described in here. It's described in ci instead of x. So the function would be 2x cubed minus cosine pi x. So that is your definite integral. Integral 2 to 5 of 2x cubed minus cosine pi x dx. And finally here, we're going to sketch this region and then use a geometric formula to evaluate the integral. So we're going to evaluate the integral by geometry. So this integral, maybe it doesn't look like something that's so clear. But remember that this is y equals the square root of 9 minus x squared. Now I don't know what that looks like. I can square both sides. Now the only issue is y has to be positive here and doesn't seem to have to be positive here. So I have to insist that it has to be, well, at least not negative. All right, so what is this? Well, if I add the x squared over, I get x squared plus y squared equals 9 with y greater than or equal to 0. that is just a circle. So this is a circle of radius 3, and I just want the part on and above the x-axis. So 2, 3, 1, 2, 3, 1, 2, 3. So it would just actually be this semicircle. Okay, so the area here is going to be 1/2 the area of the circle, which would be pi r squared. Oops. So that would be 1/2 pi. The radius is obviously 3 here. So we end up with 9/2 pi. So there we go. So that means that the integral from -3 to 3, the square root of 9 minus x squared dx, is 9/2 pi. So we're able to solve the definite integral through geometry here.